Okay, in this video we'll define rotational work and rotational power. So work is really defined the same way it was for linear work. Work is the component of the force which is parallel to the displacement times the displacement. But for rotational motion, you see that the displacement is going to be tangential, right? It will always be tangential along here. And so the component of the force which is in the direction tangential, so in the same direction as the displacement, would have to then be perpendicular to a radial line. And so we can say that the net force, or this force parallel, is perpendicular to, the radius, right? But we also know that torque is a perpendicular component of a force times this radius. And so we know that this force perpendicular is equal to the torque divided by the radius, right? So the component of the force which is parallel to the displacement is also perpendicular to a radial, to the radius of the radial line. And so then this is actually, although this is a perpendicular force, perpendicular to the radial, it is parallel to the displacement. And so the force, the net force we have here, is actually the torque divided by the radius. And then we can look at, remembering back to how we defined a radian, remember that an angle measured in radians was the arc length divided by the radius. So this meant that the delta S that we have up here, this displacement, is going to be equal to the radius times a change in angle. And so putting these together, we can see here that the perpendicular force times the displacement, which is what we call for work. So remember, our work is a parallel force, the force parallel to the displacement, but we said this was actually the torque divided by the radius, and the displacement that it goes through, this should not be a vector, the displacement that it goes through is the radius times the angle theta. So this is times r delta theta, and the radius cancel out, and so we have the work done for rotation. The rotational work is equal to the torque applied through an angle, so tau delta theta. The units for this are exactly the same. It's still a force applied through a distance, the same as we defined it before in linear terms. So this is still remember, torque is Newton meters, right, already, and then it just needs to be applied through some angle, radians, which are actually unitless. So the units of this are still Newton meters, which are joules, but since this is work, we will use joules as opposed to Newton meters for this. So the work done in rotation using rotational quantities is just the torque applied through an angle, which is everything that we would expect with making our transitions or our translations between linear and angular terms, in which case we, instead of using a linear displacement, we use an angular displacement, and instead of using a force, we used a torque. If I then just make these replacements in for our definition of work, we can see that delta theta takes the place of S, and tau takes the place of F parallel, and we have this is the work in rotation, and the units are joules. And power is defined to be the rate at which work is done. So this is the change in work over our time, or how much work is done over a time interval. So this is equal to, work is tau delta theta over a time interval, and delta theta over delta t is what we previously defined to be omega. So we have the power, the rate at which work is performed, is a torque times an angular velocity. And so the units of this are joules per second. So the units of energy or of work are joules. So this is joules and this is seconds. So the units here are joules per second, which is what we define to be a watt. So 1 watt is 1 joule per second. Power is the torque times the angular velocity, or the rate at which work is performed, and its units are joules per second or watts.